left off, this is on page, what page is this? 135. We had a couple of clicker questions. I think we hadn't done these, am I right? Remember on these, as you're, here I want to know theta 1 is 30 degrees. I want you to calculate then what is theta 3. So I know this angle is 30. What is this angle going to equal to? Don't forget your law of refraction, that n1 sine theta 1 is n2 sine theta 2. If you think you need to go through and calculate what theta 2 is, that is, if you think you need to go through and calculate what this angle is, think back to the previous problem where we're trying to figure out how these two angles were related to one another. Remember we did something to the middle section? Remember using your law of refraction here. All right, let's do about 10 or 15 more seconds. I'm going to stop at 2:15. 2:15. Okay, good. I think A is right. Let me show you. You can get rid of the second median. It's not even important. It doesn't have any impact on what the relationship of theta 1 to theta 3 is. Let me show you how that's the case. Now you can say, if I call this theta 2, you could say n1 sine theta 1 is equal to n2 sine theta 2. But then you could go on further say n2 sine theta 2 is equal to n3 sine theta 3. So we can just deal with these two equalities, that those are equal to one another. And so the way we'd go about solving this is we'd say 1.2, that's n1, sine of 30, that's theta 1, is equal to 1.1, that's theta 3, sine of theta 3. And then we do the inverse sine of 1.2 sine 30 divided by 1.1. You would find that quantity and then do the inverse sine of it. And is that 33 degrees? I trust 81% of you. That is 33? It is. Okay, I think it is 33 degrees. And then we find that that's 33 degrees. Make sure you're in degree mode on this stuff. Okay, we're not going to use radian mode at all, but if you're in calculus, you might be using radian mode. So if you're in calculus, make sure that you're switching back and forth for your calculator. And then you use your inverse sine to find the angle. Also notice here that as I move from a low index to a high index, I bend towards the normal, and then I move from a high index to a low index, I bend away from the normal, just like we talked about last time. I think I have one more here. Oh yeah, we did one similar to this with the fish. This person is looking at a star in a box filled with water. The actual position of the star is shown. Where does the person see the image of the star? This question always makes me sad? Because of the guy. Like, I don't even know. I guess I was having a bad day when I wrote this. Doesn't he look sad? Your test will be much happier. All right, looking good. I'm going to stop at 55. 5 more seconds. 55. Okay, good. C is right. Some of you put to the left. But think about how the light goes out of the water. The light comes up, and then it bends away from the normal and goes right up his nose, just like that. And it goes to his eye. And then you imagine, where does this refracted ray trace back? And that's where your brain tells you the image of the star, where the star actually is. But there's this really cool thing. You can impress your 6-year-old cousin or whatever with this. Take a cup and put like a pebble or a coin or something in the bottom of the cup. And place the cup sort of right here so that you can't see it. So that you can't see the pebble. Right? And then what can you do to allow you to see the pebble in the cup? You can pour water into the cup. And the pebble will just sort of mysteriously appear. You follow what I'm saying? Put like a dime or something in the bottom of a cup, and then move it far enough away from you so you just can't see it, so it's not visible to you anymore. And then take a pitcher of water and fill up the cup. And then you'll be able to see the cup, because the light rays will be bent. See, this person can't see. Well, he can't see. Let's say that the side of the cup was raised up a bit, so that a light ray from the star isn't going to reach his eye, but a light ray from the image of the star will reach his eye. The light is actually bent by the water when it moves from the water to the air, through the water-air interface. We'll see that. Actually, no, I have a video. Let me show you. No, I'll hold that. I'll show it to you in a bit. Okay, so total internal reflection is very similar what we've been talking about. It's a special case, really, of refraction, a special case of the law of refraction, where the angle, the refracted angle, is 90 degrees. So we're dealing with n1 sine theta 1 equals n2 sine theta 2. We're saying now that theta 2 is equal to 90 degrees. And so when I have this, when my theta 2, my refracted angle, is 90 degrees, then that means we call that incident angle, when theta 2 equals 90, we call that the critical angle. I think there was a problem on your tutor where you had to just calculate the critical angle, and you'll have to do that for the test too, by the way. I'll give you a couple of media, say glass and air, and I'll ask you, what is the critical angle for this scenario? So let's find what is the critical angle for this scenario. Well, the critical angle will be theta c, which is theta 1 when this occurs. When the light ray comes out of the glass and bends, is it going to bend away from the normal or towards the normal, going from glass to air? Think about your wave model and your tank or your marching band or whatever. It comes here, is it going to travel faster or slower in air? Faster, because I'm going from a high index to a low index. So it's like going from muddy field onto asphalt. Travel faster there, so it's going to move towards or away? Away from the normal. It'll move away from the normal. And in fact, if your angle, theta 1, is at the critical angle, it will move like that, so that my angle is 90 degrees. And so if I want to calculate my critical angle, I say n1, that's 1.3, times sine of theta 1, but I'm going to call it theta c now because that's what it's going to be, is equal to n2, which is 1, this is n2 up here, times sine of 90. And then I can solve for my critical angle. Theta c is going to be the inverse sine of 1 over 1.3, which is 50 degrees, I guess. So that is my critical angle. It might be on your equation sheet that this is listed as the inverse sine of, what is that going to be, n2 over n1. I forget, or I might not list anything, because really the critical angle is just a special application of the law of refraction. Is this on your equation sheet? Is anybody looking? Is this on your equation sheet? It might not be. It is? Okay, this thing right here. Yeah, so this is referring to the critical angle. But notice that it's just a special application. It just says that theta is equal. So you need to know how to calculate the critical angle, and then also know about this, that this is what happens is that my second angle, my theta 2, goes to 90 degrees. Also notice that if I'm moving from air to glass, what happens? Can I have total internal reflection if I'm moving from a low index to a high index? Well, you want to ask yourself the question, is it going to move, if I'm moving from air to glass, is the light ray going to move towards or away from the normal? It's going to move towards. So that angle will always get smaller. It will never reach 90 degrees. So you cannot have total internal reflection if I'm moving from a low index to a high index. Let me write that down. You cannot have total internal reflection if moving from low to high index. Is it two words or one word in this case? Is it can, not, or cannot? I'm just going to sort of put a small space between the words, and then you can decide for yourself. What was it? Cannot have total internal reflection if you're moving from low index to high index, because you're bending towards the normal, not away from the normal. And in fact, if you had something like you're going from 1 to 1.3, that would change this equation. It would be the sine of 1.3 over 1, and your calculator wouldn't give you a value for that. It would say error, go to error, whatever. It wouldn't give you a value. So if that occurs, just stop for a minute and ask yourself the question, am I really getting total internal reflection here? Is it even possible? I have a little clip about this. It's very interesting, I think. Moving from water to glass, what must theta 1 be for total internal reflection to occur? What is theta 1? All right, y'all be finishing that up. I want to look, find another video. All right, let's stop at 105. 105, just 5 more seconds. We're doing pretty well. 105. Okay, good. A is right. What? What do you call a dinosaur with a really good vocabulary? A thesaurus. Okay, but because I'm moving from low index to high index, I'm moving from 1.3 to 1.5. The light ray comes along here, it slows down, so it's actually going to bend towards the normal. But remember, if you go back and you try to find the index of refraction, 1.3 sine theta c is equal to 1.5 sine of 90. If you try to solve this for theta c, you'll find that there's an error when you do this in your calculator. So if that occurs, just step back and think, well, maybe, I'm making a mistake somewhere here. Okay. Electromagnetic spectrum, we talked about this last time. Did y'all do this one? No, let's try this. And know your electromagnetic spectrum in order of energy, wavelength, and frequency. Be able to organize them in terms of energy, wavelength, and frequency. All right, let's stop at 45. 7 more seconds. 7 seconds. 45. Okay, very good. A is right. You want to know these in terms of energy. So this is the energy. This is low energy for A, and this is high energy. So your energy increases as you move along the spectrum. Your frequency is also going to increase. Frequency and energy, did you know that energy is proportional to frequency? It's E is equal to HF. You might have seen that before. And then also the wavelength, on the other hand, decreases. So you got long wavelength. Radio waves can have wavelength, kilometer-long wavelength. You can have immense radio waves that travel around the Earth or even travel past the Earth, like can even be as big as the Earth. Our gamma rays have a very, very small wavelength. All right, so A was right. Did y'all do well in that one? Oh, you had 100. Okay, yeah, awesome. That's pretty what? Yeah, that's perfect, in fact. All right. This is kind of personal, and you don't have to raise your hand or anything. But have any of you ever had a bladder infection? If you did, you're in trouble. Okay, let's look at dispersion. Yeah, drink up, y'all. Drink all that water. Okay? The index of refraction depends on the wavelength of light. So this is for glass, for example. When I have short wavelength, I got a big index of refraction, but long wavelength, I have a short index of refraction. By the way, if these were, say, I don't know, red and blue colors, what would this be? Would this be red or blue? What, red or blue? Blue. Yeah, it's going to be blue, right? Because short wavelength is high energy. Long wavelength is is low energy. So this would be blue, and the longer wavelength would be red. This will be blue, and this would be red. You can go back to that arrows that we drew. I'm going to go back up. I'll come right back. But we have Roy G. Biv in our visible spectrum. This is low energy. This is high energy. All right, if I look at these arrows that are drew on this problem, I have on the energy, I have Roy G. Biv sort of there, increasing in energy as you go up. You know, think UV rays, right? That's just to the short of, or just along the just shorter wavelength than violet rays. They are higher energy. They give you sunburn. So with materials like glass, almost all transparent materials, they have an index of refraction that depends upon wavelength. And that allows us to have dispersion, or where we get light that's spread out into its colors. This is called dispersion, where the light is spread out into its colors. And we can use this fact about materials to construct a spectrometer. It takes white light and spreads it out into its different colors. Actually, Newton was one of the first people to do this, or first people to study how white light is spread out into its colors. And he actually thought that it was, remember Newton thought light was a particle? He thought that it was, this white light was made up of little particles of different colors, and that when you used a prism like this, it just sort of separated those different particles. It separated the blue particles and the red particles and the yellow particles. And then he also was able to recombine the particles and produce white light. But we know now that that's not the case. That it's actually a wave, at least in terms of refraction, that it acts like that, and it separates them into their different wavelengths. Okay? Here's a little coloring sheet, so now pull out your crayons, and you can color the rainbow in the proper order. Really do good. Alright, I'm going to take a nap. In 4th grade, we did that. My teacher would take naps while we all colored the state birds. All 50 state birds we had to color. This crowl. Okay, rainbows do a similar thing. Light enters into a raindrop, and it bounces around in the raindrop, but because of the wavelength dependence of the index of refraction, it separates it out into its colors. And that's how you get rainbows. I have a video here about rainbows. Let's watch. Did you know that... Oh, we'll just watch. I'll let y'all watch. Okay, let's try this quick test. Alright, doing pretty well. Turns out that all of these are true statements. All 4 of these are true statements generally, but only one of them is the answer to the question. I'm going to stop at 52. 52. Okay, good. C is right. As I said, all of these are true. Prisms are usually triangular, though you can get, like a raindrop, you can get a prism through a circular thing too if it's set up just right. The index of refraction is higher for glass, and light does travel slower in glass, but it's only because of the wavelength dependence that you actually get these light dispersing prisms, this dispersion. Hey, do you know what a clock does when it's hungry? Do you know what a clock does when it's hungry? It goes back for seconds. I'm going to miss y'all. We're almost done with the class. Alright, let's see. Make sure you go through the homework. Make sure you go through the tutor questions as well. I'll look at both for the test. Now we're going to move into Chapter 7. Anything outstanding from Chapter 6? You feel sort of comfortable with it? We have reflection and refraction. Reflection, you'll see the law of reflection. With refraction, you'll see the law of refraction. You need to know how to light bends through different media. You need to know about dispersion and total internal reflection and the electromagnetic spectrum. But that's all there is in Chapter 6. In Chapter 7, let's see, what's today? Wednesday? And we have Friday, and then Monday and Wednesday. I think we're only going to do mirrors. Right. And then we'll pick up lenses on the next exam. I think that's what we did last semester too. So if you're following along in last semester's exam, at least sort of the same layout. So we'll only see mirrors from this chapter, no lenses. If as you're going along and you run into lenses, we're not going to do that. We'll just sort of, even if we get to it, it's not going to be anything. Okay, dokie? Alright. So let's, mirrors are kind of fun. It's sort of like circuits, where you just sort of have a few rules that you need to follow. There's really just 1 or 2 equations. And then, once you apply those rules to your systems, things begin to work out. Alright, so for mirrors or lenses, we need to define the object and the image distance. And the object distance we should call this P, is the distance from the mirror lens to the image, to the object. Mirror is the distance from me to the mirror. That's our object distance. The image distance is the distance from the mirror lens to the image. All right, so mirror, object, this is our p-value. Image distance we call q. Here's my image over here. Those of you in the lab, you've done this where you actually measure p and q. Our object distance is called p. Our image distance is called q. Sometimes other books might use do and di, but I'm not. I'm going to use p and q. That's sort of standard. I don't know why p or q. That's just sort of what they use. Object distance is p, image distance is q. And then we have some rules about what the signs of these things mean. If q is positive, the image is a real image. And real images can be projected onto a screen. This right here, real image. Right? It's projected onto a screen. There's a lens up inside the projector, and there's a light bulb behind it that projects this image onto the screen. It's a real image because it can be projected onto a screen. This image, I'm not going to show you because it's a bad hair day for me. But this image, real or virtual? Excuse me, is this a real image? No, because I can't project it onto a screen. Now, if q is negative, the image is a virtual image. And while you can see the image, you cannot project it onto a screen. This is like the image in a flat mirror. So the image of a flat mirror is always a virtual mirror image. Flat mirror. So, if q is greater than 0, real image. If q is less than 0, virtual image. Real images can project. Virtual images cannot project. But it's very important to remember these sign notations. We'll use them later. They'll be important that you keep those consistent as we move throughout. And later I'll put them all in a table for you so you can see them and sort of keep them in a handy place. Now for flat mirrors, the following is true. That Q is equal to negative P. Well, you know if you look in a flat mirror, right, that in a flat mirror, it looks like you're just as far away, your image is exactly the distance behind the mirror as you are from the mirror, right? Okay, so Q is equal to negative P. The negative comes about because our flat mirror has, this is my P, this is my Q, but Q is negative because it's a virtual image. All right, so a flat mirror produces a virtual image. We will also say that a flat mirror produces an upright image. Okay, that means that it's upright, like it's in the same orientation as me. I'm standing up, and so my image is also standing up. But we'll see that some mirrors don't produce upright images. They produce upside down images. It's also an image that is the same size as the object. All right? Is it really the same size as the object? Does your head really appear the exact same size as it is in a mirror? Have you ever thought about this? Like I have this mirror. You look at it, and I put some glasses on it, like some sunglasses. Hold the mirror so that you can see the sunglasses on your face. Actually, let's hold off. I'm going to pass it around in just a minute. Let's look at magnification first. All right, so we can define magnification in two ways. The first way is to compare the size of the object and the image. So we would say the image height divided by the object height. That would be HI over HO. The magnification is the image height divided by the object height. And also the values for the magnification have these meanings. If the magnification is, say, 2 or 3 or 4, that means that the image is bigger than the object. If the magnification is less than 1, it's smaller than the object, if it's still positive. If it's equal to 1, it's the same size. Flat mirrors equal to 1. Upright mirrors, or upright images, they have a positive magnification. Inverted images have a negative magnification. So let's say, for example, I have this object right here, and then over here, this is my image. This is my object. There's some mirror. It's not a flat mirror. It's something else. Does this have a positive or negative magnification? Positive, because it's upright. So I have a positive magnification. And is that magnification bigger or smaller than 1? It's bigger, because the image appears bigger than the object. So I have a positive magnification, and m is bigger than 1. On the other hand, let's say that I have this, and then that's the image. Positive or negative magnification? Negative magnification is the absolute value of that greater than or less than 1. It's less than 1. So like it could be, for example, minus 0.5, or minus, it looks like about minus 0.5. But he's about half the original size of the object. We can also calculate this based on the image and object distance. So we know that flat mirrors have a magnification equal to 1. But more about that in just a second. Flat mirrors have a magnification equal to 1. That means that the image is always the same size as the object. And we also know that P, how did I say it? Q, rather, is equal to negative P. Because of the whole relationship between the virtual, it produces virtual images, and so you have to negate that P value to make it negative for Q. So you can probably imagine the ratio that you'll have for the magnification of a flat mirror is going to be negative Q divided by P. This is on your equation sheet. All right? So just to summarize, we have for flat mirrors, we have Q is equal to negative P. That means it's virtual, a virtual image. If it's virtual, it's located behind the mirror. Y'all ever see, what's that movie? Poltergeist? I think they might have a new rendition. I saw it when I was like 8, because I watched a lot of inappropriate things when I was a kid. But I'm not bitter about it. Anyway, what was I saying? Oh, the space behind the mirror. This is the mirror, right here. This is sort of where you stand. I like to call this the real space. But like in Poltergeist, where all those creepy people were living, that's like the virtual space. So the back side of the mirror is the virtual space. The front side of the mirror is the real space. Also for flat mirrors, the magnification is equal to 1. You have image same side as the object. And it's upright. But as I said, is the magnification really 1? It is in the sense that, like if I'm this far away from Emily, her head looks to be about a thumb tall. Can I get closer to you? But if I get closer to her, her head is now 2 thumbs tall. You know what I'm saying? Like her angular, the way her head appears to me. Back here, you're 1 thumb tall, your head, and up here, you're 2 thumbs. Your head is 2 thumbs tall. It depends upon where I'm standing as to how big her head appears to me. You have a perfect idea, right? It's not big or small or anything. That's right. Okay? And the same is true for mirrors. Look, I'm back here, my image is back here. And that ratio of distances is always going to be the same. In fact, I look twice as far away from my image as I actually am. So that means that my image is going to be half the size of my actual head. Does that matter if I move the mirror away? Well, did you ever notice? Your head stays the same size in the mirror, no matter where you hold the mirror. Your head will always stay the same size. So I put some little glasses. These look big or small glasses? They look big or small? They look small. In fact, they're half the size of regular glasses. I made them half the size. I look at my wife's glasses on, but what's the half the distance? So you can sort of get to squint one eye, and look, the glasses fit you. But then try moving the mirror out and squint one eye, and the glasses still fit you. You understand what I'm saying? Like you put like you're wearing your glasses. It doesn't matter where the mirror is, you're still going to appear the same size. Because it's like your relative distances are still the same. So y'all can pass that around and look at it. And the other thing is, I asked somebody this yesterday. I know that y'all do, like you often use your camera, and I do too. I use my camera to fix myself or whatever. Y'all ever do that? Do you look bigger or smaller in your selfie than you do in the mirror? What do you think, China? You just saw the mirror. Do you look bigger or smaller in your cell phone than you do in the mirror? Or the same? You do look smaller. Because this isn't a mirror, y'all. In fact, y'all, I know y'all are using this as a mirror, but you all look smaller than you actually are. So now your hair's all messed up because you've been looking at it. I know, I'm always going to do this, right? Okay, yeah. Hopefully it came out okay. But look at that. Look at your... Folks, I'm sorry. I don't think y'all got in on it. All right. You got to get up close on those things, y'all. All right. Let's draw a ray diagram for a flat mirror. And this isn't terribly important. You'll do this in lab, though, but it's not terribly important. But it will be important sort of when we get into spherical mirrors, because the ray diagrams will work similar to how these work. First of all, you just need to remember our law of reflection, that theta I is equal to theta R. That's true for all reflective surfaces, whether they're flat or curved, they're all going to be theta I is equal to theta R. And so, we'll imagine that we have a ray. The ray comes to the mirror. This is my theta I. Remember, I always measure it from the normal. And this is theta R. Now I can draw a second ray, because this star, right, is putting out light rays in all different directions. So I can draw a second ray that looks like this. So notice now my incident angle, theta I, is bigger, so my reflected angle will also be bigger, theta R. And now, this is where it's going to be a lot like our spherical mirrors. I'm going to trace back the reflected rays. Watch and be amazed, because it'll show me where the image is. I'll trace this ray back. We call this, by the way, a virtual ray. And I'm going to trace this ray back. And if I've been careful with the way I'm tracing my rays, it'll show me exactly the distance, the position of the image. So this is my value for P, that distance, and this is my value for Q. It's pretty good. It's not exactly right, because P and Q should be equal. But notice that they're always exactly opposite one another. It doesn't matter where you stand, they're going to still be opposite one another. And that P is equal to the magnitude of Q. They have the same value. All right, notice where the virtual rays crossed. Where rays cross is where I have my image. Now go down from here. All right. Let's take this quick test. Where does person 1 see the image of the rock? I have two people, and it says person 2 sees the image of the rock at C. So this person sees the image here. Where does this person see the image of the rock, or the star, or whatever you want to call that? Where does person 1 see the image of the rock? Just another second. Sorry, I'm trying to look at something. All right, let's stop at 148. 148. All right, good. C is the right answer. You would think that the image would shift around, but look at your flat mirror. It doesn't matter where you're looking. The image is always going to stay exactly opposite the object. All right, what is the magnification of a flat mirror? It's 1, -1, 1/2, 2. So it depends on the distance, maybe. Object. Right? What is the magnification of a flat mirror? All right, I'm going to stop at 30, and then we'll stop there actually. All right, y'all have a great day. It is 1, by the way. Y'all have a good day. I'll see you Friday, okay? And we'll do spherical mirrors. That is going to be on the exam next week. Spherical mirrors will be on the exam.